All right, so in this video, we're going to take a look at these two sections. We're going to talk about power functions, and then we're also going to talk about direct and inverse variation, which are very connected. That's why we kind of have them together. There's the starter here. It says explain why you might choose to fit either a cubic or a quadratic curve to the points below. You could certainly understand quadratic because the path follows a parabola shape. Right, like generally I kind of see this shape of a parabola if I draw it that way. But I certainly might actually think it's more cubic because since there is a single maximum and it is not symmetric about that maximum, I might choose cubic, right? So like for it to be symmetric, I would draw like a vertical line here and it would be equal on the same sides, and it's not. And so if you kind of have this one maximum, but your graph is a little skewed or it's, not symmetric, then a cubic function would actually potentially be a better one. So then they go on to say, okay, well, theory suggests that it will be one of these two, right? They end up doing a quadratic and they end up doing a cubic. And so it says, given 4 points have these coordinates, so they give you A, B, C, D, find the sum of the square residuals for each of the curves and say which one is better, right? And so we can do this kind of in a single calculation. Remember, we set up tables, but you could also do it, the sum of the square residuals for the quadratic is going to be the difference in the x and in the function values and the given points. So I'll put the given points first. It doesn't matter which one you put first. And then if I put 1 into this equation, I get out 2.5. And so we'll just go through and kind of write out what all these are, right? Instead of actually calculating them. Right, we would take the 4.5 that is there, put in 3 into this equation, and figure out what it is, and it's 5.1. That's why I wrote the 5.1. So I find the difference of all these things, then I square them, and then I add them all together. So this is why I'm doing it in a single calculation. So then I find the difference of the actual y value, 4.3, minus 5 substituted into the quadratic, which is 4.5 squared. And then the last one is actual y value of 1.7. And then when I put 6 into the quadratic function, I get out 3 squared. And so I end up with 2.34. And so then I would do a similar thing with the sum of the square residuals for the cubic one. Always starting with the actual y value. That's what I've chosen. And then when I put those values in, I get minus 0.789, that squared, then the actual y value of 4.5 and its difference with 4.331 squared, and then 4.3 minus 4.225, right? I'm getting these these model y values, these ones, by putting in the x value into this equation, right? Like I'm not showing you how to get that. You would go in the calculator, you would grab that point. And then plus 1.7 minus 0.509. Can't read my handwriting, but I think that's what it is. But then overall it equals 2.94. And so we can see that the better of the two models is definitely going to be the quadratic because it has a smaller sum of square residuals. Right? So it means it's closer to a quadratic than it is to a cubic. But there may be real world context as to why you might choose cubic instead, even though it has a lower, and we can explore those in a little bit. So then it says find the least squares cubic regression, right? So this is in your stats2 variable. Enter your data, make sure you're on cubic. It's asking for the equation. So it would be y equals, if you put all that in there, 0.0992x cubed plus 0.555x squared plus 0.319x plus 1.23. Okay, so you get this long cubic function. It says state the r squared value and say what this indicates. If you go find that r squared value in the calculator for that set of data, it is 1. And it means that the curve fits the data points perfectly or exactly, right? Like it fits it. I can draw a cubic one that fits this exactly. It goes through all all 4 of those points exactly. And so it says, given the points represent the height of an object thrown from the ground level at time t, state one reason why either of the first 2 models might be preferred. So now here's some real world context. Right, and so we should think, okay, well, if it's thrown from ground level, right, maybe we choose one of the ones they gave us up here. Right, so because thrown from ground level, like we know that, it says it right there, we want a y-intercept of 0, which the regression one does not have. It says it starts at 1.23. Whereas these other 2 up here, this one and this one, don't have y-intercepts, or the y-intercepts are 0. And so then it would maybe make sense to choose from one of those 2. And if you're choosing from this one or this one, maybe it makes more sense to choose the quadratic. You could also say something like, I know that projectile motion is quadratic. And so then it makes sense if there's no other forces acting upon it. Quadratic might be the better of the 2. Okay, so this section is a spreadsheet thing. We're actually going to skip this. We will skip and come back for your IAs right in the spring. We'll kind of like revisit this idea of doing it in a spreadsheet. It's not something that you have to know how to do for the test. You're not going to be asked to use Excel or anything like that. So don't worry about this for the test. What could be on the test are these things called power functions. And so power functions are in the form a times x to the p, when p is bigger than 0, so p has to be a positive thing, and the function must start at 0, 0, right? Or 0, 0 must be part of the function, right? This is the point 0, 0. It has to be a function. So when p equals 1, the function is linear, right? A times x to the first is just ax. That's a linear function. When p is equal to 2, that's an example of a quadratic. When p is 3, that's a cubic, the most basic quadratic and cubic functions that we can think of. So here it says, let's sketch these things, kind of in this investigation. It says, let's sketch what happens when you have squared, cubed, to the 4th, to the 5th, to the 6th, to the 7th. And so what you can do is go put all of these in your calculator, right? Go f1 of x is x squared, f2 of x is x cubed, right? And so on. And take a look at them. You don't need to sketch them, right? Just look at them in your calculator. And then it says, can you group these? So once you've put those in, maybe pause the video and put them in so you can look at them. But once you've done that, take a look at, it says, can you group these into smaller categories? And so what you'll notice is that even powers have a parabolic shape, whereas odd powers have sort of a cubic shape, right? But it could be like kind of flatter, right? It's a cubic, but they're doing this, this kind of shape when we look at them. And so it says, how are they the same? How are they different? So you'll notice that the higher powers, maybe the higher powers have some flatter sections. right? Like they get flat along the middle for longer. So they kind of like rise up, they get flat, and then they continue to go up. Then it says, how are they the same or different from the parabola, right? Like this is the idea, they look like a parabola, but they have these flatter bottoms, right? Like something like x to the 10th would look like this, right? Like really flat on the bottom, but still kind of curves and does this parabola shape. How are they similar and different to the cubic function? Well, it's the same thing, right? So it's the odd powers look cubic, but are flatter around the origin. Right, so this is what I drew before, like something that just kind of gets flat. If you do x to the 17th, it's going to be this really weird flat function that's that looks like it's flat in the middle, but then rises on the left, or rises on the right, falls on the left. Yeah. So then it says for 5, how many maximum and minimum points can a power function have? Right, it can only, for even ones, it can have only one. Right, so to answer this question, for even power functions, it can only have one max or min. For odd, it can have, the ones we're looking at have no max or min, right? They kind of like rise forever, right? They increase forever or they decrease forever. So they don't have this true maximum and minimum. And they said, oh, the power function's symmetric. And yes, so what type? So they are symmetric. The even power functions are symmetric about the y-axis, right? Like the y-axis cuts them in half. The odd power functions have what's called rotational symmetry of 180 degrees around the origin. So if you were to rotate these things 180 degrees around the origin, they would be the same function, right? Like that's the symmetry that exists for them. Yeah, and then it says what happens to graphs of the power function as the power increases. We kind of already said this, they become flatter around the origin. Right. So let's take a look at kind of an actual example of this. So here we have this bowl. Designer wants to create a model function for a bowl that she sketched by hand, and in order to be able to process it digitally, so she's marked all these data points. The center is at the bottom, right, like the letter I that you can see there, and all the data points are here. It's just data points split up into 2 tables. So you have all of A through Q, right, all of these data points here. So part A says plot the given data in your calculator. So you have to take all of that data and go put it into stats2, right? So we're going to take this and go put it into stats2 variable because you have an X and a Y. And so once you've done that, to pause the video, go toss those in because you're going to do a lot of calculator manipulation with it. So she first thought of using a quadratic model, which maybe makes sense, right? Like it has this curve, a single value there, it's symmetric around that, but it does get flatter at the bottom. It's a bowl, right? Like it should be flatter down here and increase more here. So maybe a higher power is better. But here it says, B, let's explain the reasoning for quadratic. It certainly has one minimum and is symmetric about that minimum. Right, so a quadratic would certainly make sense for this. So then it says use the calculator to find a quadratic model. So you're gonna change this, make sure when you go to, once you've entered the data, which you should have already done, hit symbol and make sure you choose quadratic to go find that equation. And so you'll end up with this. It is 0.0263 x squared. There's actually not an x term in this one. It's 0x and then minus 1.15. So then part D says, assess the choice of the model by determining the coefficient of determination. Right? Coefficient of determination is R squared. So if you click stats on the screen, you'll find 0.933, which means the data fits the curve very well, right? Like that's really close to 1. So would be a good model. There's nothing wrong with that quadratic model. So then it says, sketch the model of the function over the scatter plot and comment on the closeness of the fit of the data. So this you can do by hitting fit, right? So when you click for part E, you're going to go to the calculator. I don't have the data in there, but if you have data in there, you can look at it, and if you click plot, it will plot the data and you can see it. And then you go menu fit, turns that fit on and off so you can see how well it fits, right? This is not that data from the question, but right, so you go to plot and then fit. We'll turn that equation on so you can kind of look at it. And then it says comment on the closeness. Right, it fits very well, except you'll notice at the bottom of the bowl. Right, like it does well on the sides, but not on the bottom. Right, so it fits well on the sides, but not the bottom. Okay, so not being satisfied with the model function she created, she decided to determine a new quartic, right? So like these words are really close. Quartic is a 4th degree model, right? Quartic is not quadratic, it's raised to the 4th. And it says, explain why the designer might have not been satisfied with the model function she created and why quartic is better. Right, quartic makes more sense. So quartic, because it is flatter on the bottom, right? It will create this bowl shape, this idea of like a bowl is kind of flat on the bottom so that it can sit on a table or whatever. Okay, so then G says, let's go find that thing, right? Use your calculator to determine the quartic model. So all you're doing, instead of going quadratic, you're gonna go change to the option of quartic, right? So when you go to symbol, you're gonna choose quartic is down here below cubic. They're in order, right? Quadratic, cubic, then quartic to the 4th. And that model is g of x equals 9.46 times 10 to the negative 5th. Like it's a bunch of zeros. X to the 4th plus some other stuff, right? It's a really long function. You don't need to take the time to write it down because you're just going to do all the stuff for it in the calculator. But as long as you got that first number correct, right? Like if you did it and you got that number as your first number, then you know you've done it correctly because all the others will be correct. Okay, so then H says assess your choice by looking at the R squared. So R squared for this one is 0.9999, what is that, 4 nines? I think a 4 and then a 7, which if you were to round that to 3 significant figures is approximately 1. Right, like that would actually round to 1.00, right? 1. And so then it fits very well, right? We know that it's better than the other one. The other one had a R squared of this, which was very good, but this R squared is better. So quartic is more appropriate. So then it says sketch the model function over the plot and comment on the closeness. So again, hit that fit button and see what it looks like. And you can see that it fits it a lot better. It will fit the bottom of the bowl better. And so then this last part says using your quartic model, which I've called G of X. My quartic is G of X, that one. The designer wanted to create another model whose dimensions are double in size to the original, right? So dimensions means both X and Y. So both X and Y. And so it says determine the equation of the model for the new function. And so this is kind of just reminding us of what transformations are. If I want this new function, h of x, it's going to be twice as big as g of x. That would account for doubling the y values. If I want to double the x values, I have to multiply by a half in there. Right? Remember, inside is 1 over a. So if I want to double things, I have to multiply by 1/2. Right, so if I took that g of x function and I multiplied it by 1/2 on the inside and 2 on the outside, I would end up with doubling x and y values. I would end up with this new function. Yeah. All right, then we have these power functions with negative exponents. So we've looked at power functions that have positive exponents, but power functions can also have negative exponents. And these are the ones that have asymptotes. We'll kind of see that there are different branches. And so again, take the time to put all these in your calculator, right? Pause the video, F1, F2, F3, right? Enter them all in so you can look at them all together. And then we're gonna see like what patterns can we come up with. So once you've done that, let's look at question 2. So question 2 says, how can you describe the shape of an inverse function, right? So we could say they both have, right? There's a difference between odd and even, right? Like hopefully you're seeing that odd look one way, even look the other. Both have vertical asymptotes at the y-axis. Both have vertical asymptotes at the x-axis. Wait, one of those isn't right. They both have vertical at the y-axis and horizontal. Horizontal asymptotes at the x-axis. Right, they're looking something like this, right? Your odd ones have two branches that are opposite. Right, these are your odds. Whereas your evens, the branches are both positive. Right, because when you square something, everything is positive. Or when you raise something to the fourth, everything is positive. But if you raise something to the third, you can still have a negative, right? -2 raised to the third is -8. So can you group these? Maybe we could describe a little bit further, right? The even ones, the function is always greater than 0, right? Like it's above the x-axis, that's what we said. And then the odd ones have the function is positive or negative, depending on what part of the branch it's on. Okay, so can you group these, right? We can group them certainly into odd and even, which we kind of already have done. Are inverse various functions symmetric? So odd have rotational symmetry about the origin. Right, so if I look at an odd one here, if I take this and I rotate it 180 degrees, I get the other one. That's that rotational symmetry. And even have symmetry about the y-axis. Right, if I was to flop this side and reflect it over to that side, they would be the same thing. Okay. And so then for 5, it says describe what happens to y values as the functions become very large. Right, so what happens to y? So as x approaches infinity is how we could write this. Right, what happens to y? Right, for a, so as x becomes very, very large, so as x approaches infinity, both of these functions, right, so that's kind of over here and over here, both of them approach 0. Right, so y approaches 0. For b, what happens as x approaches 0 from the positive side? So the positive side is the right side. So as it approaches 0 from the positive side, what's happening to y values? Approaching 0 from the positive side, y values. Right, so as x approaches 0 from the positive side is how we'd write that. Y approaches positive infinity, like it's going up forever. It's going to be these really, really big positive numbers. And then it says, well, what happens as they approach from the negative, right? So, and this is where they differ. So as x approaches 0 from the left side or the negative side, the odd functions, the y value approaches negative infinity, but for the even ones, the y value approaches positive infinity. Right? And it's because the even functions go up, whereas the odd functions go down. Okay, and then our last one. What happens to the graph of an inverse variation function as the values become more and more negative? They basically become steeper, right? So they become steeper. If you were to do 1 over x to the 100th, right? then you would end up with this really steep branches that you might not even be able to see on the calculator, but they're just getting steeper and steeper because they're growing so quickly. Yeah. All right, so let's take a look at this function here, or this question here. We can take a look kind of at these inverse ones and what questions might actually look like. So here it says, consider this function f of x equals 1 over x when x is not equal to 0. The graph f of x is transformed and becomes the following functions. Give a description of the transformation they represent, and then write the function down the equations of the asymptotes of these transformed functions. So the first one, if I start with this, 1 over x, what happened to it if I subtract 3? Right? So if I take the whole function and I take away 3 from it, right? This is a vertical translation down 3. Right, and so then all of its asymptotes would be down 3. So the equation would be 1 over x minus 3, right? So the vertical asymptotes are affected, or sorry, the horizontal ones. The horizontal ones are down 3. The vertical asymptotes don't move because they are affected by x values. So then B says, okay, let's have this h of x, and it's f of x minus 3, but inside the brackets. And so this represents a horizontal translation right 3 units. And so it would take the minus 3 and put it in with the x. So it'd be 1 over x minus 3, right? Like in brackets. You don't need those brackets, but just so we can see that, oh, it's in brackets. And so what that would do is move everything 3 units to the right. So it would move the vertical asymptote 3 units to the right, and the horizontal asymptote would stay where it is. So then the last one says, well, let's do 2 things. So j of x is f of x plus 1 and then minus 2. So this means left 2 and down, or sorry, left 1, because it's plus 1, and down 2. And so that function looks like this. So j of x is 1 over x plus 1. Right, I'm affecting the x, so it goes right with the x, and then I go down 2. And so it moves your horizontal asymptotes 1 unit to the left. It moves your vertical asymptotes 2 units down. Right, so we end up with those. Okay, so varying directly, right? If things vary directly, it just means that they're multiples of each other. So here it says the rate of spread of fungus in a petri dish varies directly with the square of the perimeter of the area of the fungus, right? So if I was to write this as an equation, it would be x equals k times p squared. And so what it's saying is the rate of the spread, which is x, varies directly, so is a multiple of the square of the perimeter of the area, right? And so, which is just p. So x is a multiple of p squared. That's where this equation comes from. And so then it gives us some information. It says if the rate is 2 cubic centimeters per second, when the perimeter is 3.2. So they basically give us a p, this is a p value, and this is a x value. And so we can substitute those in and find the k, right? So 2 equals k times 3.2 squared, divide by 3.2 squared, so then k is 0.195. Right, so my actual function is 0.195 p squared when I'm given that initial set of values. So then B says find the perimeter when the rate is 6. So now I know this k value, this unknown thing that I'm multiplying by. So I have x equals 0.195 p squared. I put the 6, which is 6 is the perimeter. It says find the perimeter when the rate is 6. So that's the x value. So 6 equals 0.195 p squared. Divide by your 1.95, take the square root. So then p ends up being 5.54 centimeters. Right, that's the perimeter. Okay, so that's varying directly. When you vary directly, you're just a multiple of it. And then what we also have is this varying inversely. So when something varies inversely, it is one of the variables is in the denominator, right? So for example, here it says the number of hours it's taken to build a wall varies inversely with the number of people who work on it. And so that means the n is going to be k divided by x, right? If it varies directly, it's k times x, or whatever variable it is. If it varies inversely, it's k divided by whatever that variable is, because they're inverse of each other, right? Like they're dividing. So then A says, okay, we have this, and then they give us some information. When 3 people are available, the wall takes 2 hours to build. So it takes 2 hours when 3 people are working on it. So in this case, k is 6. So my whole function is 6 over x. But then the question asks me, find the time it takes to build the wall when 4 people work on it. Now that I know k, I can take this and say, okay, well now 4 people are working on it. So it should take 1.5 hours if I divide 6 by 4. So then it says B, given it takes 3 hours to build the wall, how many people should work on it? So 3 is in hours, so it goes over on the left side of the equation. And 6 over x, right? So 3x equals 6, x is 2, right? So it takes 2 people to make it happen in 3 hours. Yeah, and so then the last thing to look at here is just that you can do power regression. It works the same as all of our other regressions that we've done. You have all the data in your calculator from this. It's talking about this example 11, this one that was back here, right? Like you have all of this data in there. So you can hop into your calculator and find the power function that works for that. If you look at it, there is power right here, and you'll notice that it's b times x raised to something, right? That's the way the will give you your function, which is our power function. Yeah, and so you can perform the least squares regression for these points that you entered in that thing. I don't have the solution to it, but you can just look at it and get your equation if it ever asked you to do some power regression. All right, make sure you check out the homework and let me know if you have any questions.